Hello, I'm Asam, and today I'll present my work on estimating intervention target from observational and interventional distribution. Uh, Causal discovery is a task for finding the causal structure of the data. Here we have a data about a system that consists of four random variables. A causal discovery algorithm will estimate the causal graph where each node represents a variable and the edges between the two nodes show the dependence between the two. For instance, here variable z depends on both x and y, whereas x and y are both independent exogenous variables. There are different ways to learn the causal graph from the data. From the causal inference literature, the most common way is to use an algorithm called PC. It internally uses conditional independence tests to check the relationship between the variables. This equation here is used to check the statistical independence. It shows that two variables are independent if their joint distribution is the product of their individual distribution. Using this definition of conditional independence, the PC algorithm estimates the causal graph by starting with a complete graph where every node is connected to every other node. Next, it uses pairwise CA or conditional independence test between the nodes and remove the edges if they are independent. In the next phase, it tries to use conditional independence test, the same conditional independence test, but now it tries to condition on other variables. For instance, here w and y are dependent on each other. However, if we condition on z, they become independent. Eventually, it has an orientation phase where it tries to assign the direction to all the edges following some static rules. However, as we know, correlation doesn't imply causation. What it means in our context is that sometimes observational data might not be enough to estimate the exact relationship between the variable. For instance, here x and y have a correlation, but we don't know the direction of the correlation. From the causal inference side, we have a tool for such scenarios to give us more information. It is called intervention. It provides us a means to change the data generative mechanism of a node. For instance, here we set the data generative mechanism of x to be just 1 rather than a random variable, and then we saw the effect on y and eventually figured out that the dependence is from x to y, not from y to s, because if we intervene on y, the x won't get affected. Doing so allows us to use the distributional invariance between both the observational and interventional data to learn more about the structure of the underlying data. However, using just a simple algorithm to find the interventional target is not suitable because it's an expensive task in terms of time. For instance, this graph shows the runtime of PSI-PC, which is an extension of PSI-FCI proposed recently in NeoRISP 2020. Here we can see the runtime of PSI-PC increases exponentially with the number of nodes in the causal graph. To reduce this runtime, I propose a localized approach to learn the interventional target. The key idea is to decouple the task of finding the interventional target from learning the causal graph. Doing so gives us the room to reduce the runtime of the algorithm. For the implementation, I created a random tag and used a package called diagram to generate data for both observational and interventional setting. I also implemented PSI-PC and PSI-LPC. PSI-LPC is a localized version of PC. Here is a sample tag which I used to generate data. In this example, x5 is the interventional target. In my experiments, I try to vary the number of nodes in a graph and check the results, the runtime and recall. And I ran every experiment 100 times. Here we see the runtime of both algorithms. Note that PSI-LPC reduces the runtime significantly as compared to PSI-PC because of its localized approach. This plot shows that PSI-LPC provides a reduction in time while keeping the same detectability. The important thing here is that PSI-LPC provides similar recall uh, as PSI-PC. In conclusion, we saw that localizing the interventional target is a challenging task. My key observation is that we can decouple the task of finding the interventional target from learning the causal graph. Using this insight, I proposed an algorithm that systematically estimates the interventional targets with this localized approach. The evaluation on synthetic data shows that the proposed approach can effectively find the interventional target while keeping the runtime low. Thank you.